Welcome. This video is an introduction to improper integrals. Some integrals have a meaningful value, but they cannot be evaluated strictly by using the fundamental theorem of calculus part 2. Let's recall what the fundamental theorem of calculus part 2 tells us. In a nutshell, it allows us to evaluate a definite integral by finding the indefinite integral, or the antiderivative, and evaluating it at the upper and lower limits. This is the main statement of the fundamental theorem of calculus in a nutshell. However, there is a condition that must be met before we can use this formula. The condition is that f of x is continuous on the closed interval from a to b, and capital F is an antiderivative of small f of x. Let's focus on the first part of this condition. If we have a function that is not continuous on our closed interval given by the integral, then we can't strictly apply this formula. This gives us two main types of improper integrals. The first main type is when we have a discontinuity on the closed interval. In this case, the condition of the fundamental theorem of calculus would not be satisfied. Here's an example of such an integral. If we have the integral from 1 to 3 of 1 divided by x minus 2, this function is undefined when x equals 2, so it is not continuous over the interval from 1 to 3. Another example would be the integral from 0 to 1 of 1 divided by 2 square root of x dx. Once again, if we plug in x equals 0, we have a discontinuity, so this function is not continuous on this closed interval. This first integral does not converge to any value. The second integral does. The second main type of improper integral is when we have an infinite limit of integration. Here's an example of such an integral. If we have the integral from 0 to infinity of e to the negative x dx. Turns out that this integral actually converges to a finite value, to 1 in fact, but we're integrating over an infinite integral. In the statement of the fundamental theorem of calculus, the closed interval is assumed to be finite. These integrals are called improper integrals, and there are various techniques for handling them. Let's take a look at this second integral that we wrote here and see how to solve this one. We're looking at the integral from 0 to 1 of 1 divided by 2 square root of x dx. The first step is to eliminate this problematic limit. So we replace the 0 with a. Now, this integral corresponds to the following area. 1 over 2 square root of x looks something like this. And we're integrating from 0 to 1, so we're imagining this area as corresponding to this definite integral. So we first remove the problematic limit of integration, and then we take a limit as that value approaches the true value from the proper side, from the right-hand side. We evaluate this integral just as we would using fundamental theorem of calculus part 2, and then we evaluate the limit afterward. This integral, we first start by taking an antiderivative. The antiderivative of 1 over 2 square root of x is the square root of x, and we integrate from a to 1. Plug in the upper limit, plug in the lower limit, take the difference, and we still have this limit out front. Now we have square root of 1 minus the square root of a. This equals the square root of 1, which is simply 1, minus the limit as a approaches 0 from the right of the square root of a. Square root of a as a function looks like this. Here's the a axis. As a approaches 0 from the right-hand side, square root of a approaches 0 as well. So we have 1 minus 0, and our final answer is 1.